Hello everyone, I am Shreyas Kamble from Walchand College of Engineering, Sangli. This is my project presentation for the Embedded Systems Internship at Emertxe, which I completed in May to June 2025. The project is titled as Washing Machine using PIC16F877A Microcontroller. I will take you through my internship overview, the embedded systems concept, project design, development process, testing, and a demo of the working project. Let's start with knowing about the internship. This internship was a 1 month hands-on program offered by Emertxe. It was completely online using simulation tools like PixSimLab, coding on MPLab X IDE, and compiling with the Emertxe compiler. The internship goals includes first, building strong foundation in embedded C programming. Second, learn microcontroller architecture for PIC16F877A and how to program it. Third, to understand peripheral interfacing for LED, keypad, timer, LCD, buzzer, fan. To gain exposure to real-time embedded system development and to complete a fully functional embedded project as an outcome. Now let's understand what an embedded system is. So what is an embedded system? An embedded system is a combination of a microcontroller with input and output peripherals, which is designed to perform specific tasks reliably and efficiently. In my project, the PIC16F877A microcontroller works as the brain of the washing machine. It takes input from the keypad for selecting power, mode, and water level. It controls outputs like LCD for status display, buzzer for alerts, and fan which stimulates the motor. It uses timers and interrupts to manage washing stages like wash, rinse, and spin with real-time accuracy. So the embedded system feature that my project offers is first, real-time control of washing processes. Second, user interaction via keypad and LCD. Third, timer-based automation for each washing stage. And fourth, control outputs for fan, buzzer, and LCD based on user selection and process flow. Now, let us have a brief overview about my project. My project title is Washing Machine using PIC16F877A Microcontroller. The project objectives include first, to design and simulate a washing machine using the PIC16F877A microcontroller. Second, to handle real-time control for mode selection, water levels, display, buzzer, and fan. The key features of my project are first, mode selection. The user can select different modes such as quick wash, normal, heavy, spin only, or wash only. Similarly, the user also has an option for water level selection, which includes low, medium, high, and maximum. Third, we have a feature of LCD display, which show process stages like power on, washing, rinsing, spinning, and completed. Fourth, we have buzzer alerts for start, end, errors, or notification. Fifth, we have fan control, which stimulates the washing machine drum's motor. And at last, we have timer and interrupt handling, which manages process duration accurately for wash, rinse, and spin. Let me tell you about the project significance. Washing machines are a common example of embedded systems used in home automation. It demonstrates how microcontrollers automate physical processes based on user input. The project combines critical embedded system concepts like input handling via keypad, second, output control through LCD display, buzzer, and fan, and process control through using timers and interrupts for scheduling tasks. This project provides practical experience in hardware interfacing, embedded C programming, and real-time process management. Now, let's discuss what I learned during this journey. First is C programming. I learned how to structure a code, use functions, and manage variables in embedded C. Second is microcontroller fundamentals. I understood what a microcontroller is and how it controls external components. Third is PIC16F877A microcontroller. I studied about its internal architecture, input-output ports, timer, and how to program it. Fourth is LEDs. I practiced turning on and off LEDs using GPIO pins. And at last, digital keypad. I implemented input reading and differentiated short press versus long press logic. Let's discuss the tools and components that I use for this project. The hardware components. First, I used a PIC16F877A microcontroller. This is a 40-pin microcontroller. The input device that I used is only a 6-key digital keypad. The output devices that I used include first, a 16x4 CLCD display for status display. Second, buzzer which I use for alerts. And third is a fan which acts as a simulation for motor for drum operation. The software and development tools that I used include first, MPLab X IDE. This is a code development environment. Second, X8 compiler. This is a microcontroller C compiler for PIC family. And third is PIC for microcontroller simulation. This is the block diagram of my project. At the center is the PIC16F877A microcontroller, which controls the entire process. The input device is the keypad, which is connected to port B from RB0 to RB5, which allows the user to power on the system, select the washing program, select the water level, and to start or stop the process. The outputs are first a CLCD, which is connected to port D for data and port E for RE2, for RS, RE1, and EN. The CLCD displays the process status like washing, rinsing, spinning, and completion. The buzzer is connected to RC1, which alerts the user during stage changes or when the process is complete. Fan is connected to RC2, which simulates the motor operation during washing and spinning. A door sensor is also connected to RB0. The system checks whether the door is closed before starting or continuing the process. If the door is open, the fan stops, the timer pauses, and the buzzer alerts until the process is closed again. A door is also connected to RB0. The system checks whether the door is closed before starting or continuing the process. If the door is open, the fan stops, the timer pauses, and the buzzer alerts until the door is closed again. The microcontroller runs the process using a state machine based logic, where it switches between states like mode selection, water level selection, start or stop interface, washing process, and completion based on keypad inputs and timer counts. This is how all the hardware and logic blocks work together to simulate a fully functional washing machine. This is the board diagram from the PICSimLab simulator, which represents the complete setup of my washing machine project. Here, you can see a PIC16F877A microcontroller, which is the brain of the system. It controls all the inputs and outputs based on the logic written in the code. The input section. The keypad is located at the bottom left of the board. It is connected to port B from pins RB0 to RB5. The keypad allows the user to power on the machine, select the washing program, choose water level, and start or stop the process. Additionally, RB0 is used for the door sensor input. This ensures that the door is closed before running the process. If the door is open, the fan stops, the timer pauses, and the buzzer alerts until the door is closed. The output section. The CLCD display is located at the top left, and it is connected to port D for data and port E for control lines RE2, RS, and RE1. It displays status like power on, washing, rinsing, spinning, or program completed. The, the fan is located at the top center labeled as cooler. It is connected to RC2, that is port C. The fan simulates the drum motor operation during the washing and spinning stages. The buzzer is placed near the fan and labeled buzzer. It is connected to RC1, that is port C. It alerts the user during stage changes and on process completion. Timers and interrupts. Timer 2 and its interrupt are configured in the code and are responsible for process timing, controlling how long each stage runs like wash, rinse, and spin. Power and other components. The boards includes power supplies, reset button, and relays. But for this project, the primary components used are keypad, LCD, fan, buzzer, and these are controlled via the PIC controller. This diagram perfectly represents the hardware simulation environment, matching the connections and logic defined in my code. The microcontroller continuously monitors the inputs, controls the outputs, and manages the entire washing process in real time. Let's now go through how I developed this project step by step. The development process followed these steps. First is requirement understanding. I defined washing machine process flow and user interaction. This included program selection, water level, and start or stop operation. Second is component mapping. I assigned microcontroller ports for keypad, LCD, buzzer, and fan. Third is code structure design. I implemented this using a state machine model in which first the user will select the washing machine program. Second, he will select the water level selection. Then he will either start or stop the washing machine. And finally, the run stages of the washing machine. Fourth is implementation and debugging. For this, I use a timer based control. I use keypad edge detection for short and long presses and also LCD for message updates and state handling. Now, let's look into some of the important implementation details. First is power on animation. This shows welcome graphics on the LCD. Second is state transition. To scroll between programs or water levels, we need to press the switch for a short duration of time.
To move to the next screen, we need to press switch 4 for a longer duration of time. Next comes timing control. Timer control processes such as wash, rinse, and spin is managed by timer 2 based on selected program and water level. Next comes the final run. This manages the complete washing cycle. And at last comes the completion. This stops the fan, sounds the buzzer, and displays the completion message on the LCD. Now, let's discuss the challenges faced during this development and how I resolved them. The challenges that I faced were: first, keypad debouncing. Initial key press detection was unstable. This was resolved by adding software delay and state-based detection. Second, switch mode detection, that is, detection of short press and long press. It was difficult to differentiate between short press and long press. This was solved using counter-based logic in read digital keypad function. Third is timing accuracy. Delays were not realistic initially. This was fixed using timer 2 configuration and calibrating delays. Third is state transition bug. Sometimes screen didn't move forward. This was corrected by reviewing flag updates and ensuring proper edge detection. And at last was power on delay. Animation was taking too long, so I reduced the delay duration for better responsiveness. Let's see how this project was tested. All the testing was done using PICsim which eliminated the need for physical hardware. The functional screens verified: first, power and animation; second, washing program scrolling and selection; third, water level selection with short or long press detection; fourth, start or stop interface using switch 5 and switch 6; and timer countdown and phase-wise execution for wash, rinse, and spin. Outputs tested: first, fan for motor simulation; second, buzzer for completion alerts; and third, LCD which updated throughout the cycle. The bugs fixed were: first, key press debouncing; second, delay timing tuning; and third, state flag mismanagement. Let me now explain how the project works step by step. First, the user will press switch 5 to power on the system. This will show the LCD will show a power on animation. Then use switch 4 short press to control through different washing machine programs like daily, heavy, delegates, etc. Long press switch 4 to move to water level selection. Use short press again to scroll between water levels like auto, low, medium, high, and maximum. After selecting water level, long press switch 4 to move to start or stop screen. Press switch 5 to start washing cycle or switch 6 to cancel and go back. Once started, the process runs automatically through wash, rinse, and spin, with timers managing each stage. The fan runs to simulate the motor and the buzzer alerts at the end of the process. After completion, the LCD displays program completed, the fan stops, and the buzzer beeps to notify. Now, let us look at the project demonstration. First, let us begin by looking at the code in MPLABX IDE. On the left side, you can see two main folders: header files and source files. First, let us look at the header files. First, clcd.h. This file is for the LCD display. It defines the pin connections like RE2 for RS, RE1 for E1, RE1 for EN, and port D for data. It also has LCD line addresses like line 1, line 2, line 3, line 4, and functions like initialize CLCD, CLCD underscore print, and CLCD purge to handle LCD display. Next is digital keypad.h. This handles the keypad input. The keypad is connected to port B from RB0 to RB5. Functions like initialize digital keypad and read digital keypad detect key presses including short press and long press detection, which is very important for program selection and water area selection. Next is timers.h. This is for setting up timer 2. The timer is used to count seconds and minutes, which controls how long each stages like washing, rinsing, or spinning runs. Next, we have washing machine header.h. This file contains higher level function declaration include power on screen for startup animation, washing program display for program selection screen, and water level select screen, set time, run program, and door status check all control the full process. Finally, we have main.h. This file holds global definitions for state like washing program screen, water level screen, start screen, and defines output pins like fan for RC2 and buzzer RC1. Now, let us look at the source files. First is clcd.c. This file handles the LCD operation. It contains functions like clcd write,
CLCD print, and initialize CLCD for sending data to the LCD and controlling what is displayed. Next, we have digital keypad.c. This file manages the keypad input. It detects which switch is pressed, switch 1 to switch 6 using bit masking. It also has logic for debouncing and recognizing short versus long presses. Next, we have timers.c. This set this sets up timer 2. It controls the internal clock for stage timing and enables the timer to interrupt. Next, we have isr.c. This file has the interrupt service routine. Timer 2 generates interrupts and this file counts seconds and minutes. When 20,000 counts are reached, 1 second passes and updating the seconds and minute variables. This logic controls how long washing, rinsing and spinning lasts. Next, we have washing machine function def.c. This is the heart of the washing machine logic. It includes power on screen for startup animation, washing program display for scrolling programs, water level screen for selecting water levels. Run program handles the process flow checking timers, moving between wash, rinse, spin and handling the door sensor, controlling the fan and buzzer and updating the LCD accordingly. Also, we have door status check which pauses the process if the door is open. Next, we have main.c. This file controls the entire application. It uses a state machine approach to manage transition between screens, program selection, water level, start screen, and process execution. It also handles key process actions like start, stop, or cancel. Finally, I click on Build Project. This compiles the code and generates the hex file. The hex file contains the machine code to run this project on microcontroller in PICSimLab. Now, let's move to PICSimLab and see it working. Now, let us start with our PICSimLab simulation. First, we will select a microcontroller. For this, we will go to microcontroller and then select our PIC16F877A microcontroller. After this, we will make sure that our clock frequency is 20 MHz and the LCD selected is HD 44780 16x4 LCD. Next, we will load our hex file. For this, we will go to File, click on Load Hex, and then select our hex file from the desired location. Once the hex file is loaded, the microcontroller starts running the code exactly like real hardware. Now, let us power it. Now, let us power on our washing machine. So I will press our key 5 to power on our washing machine. You can see the LCD displays power on animation saying powering on washing machine. After powering on the washing machine, the next screen is washing program selection. The LCD shows washing program at the top. I will press switch 4 for a short duration of time to scroll through the available options. As I press switch 4 for a short duration, you can see different programs on the LCD like daily, heavy, delicates, whites, stain wash, and many more. Suppose I choose heavy for this demonstration. So I will press switch 4 for a long duration of time. The LCD now displays water level with options like auto, low, medium, high, and maximum. Again, I will press switch 4 for a short duration of time to scroll through the available options. For this demo, I will select medium. To confirm this option, I will press switch 4 for a longer duration of time. And the next screen will be start or stop screen. The LCD now shows press switch 5 to start or switch 6 to stop. If I want to go back and change anything, I can press switch 6. Here, I will press switch 5 to start the washing process. As soon as I press start, the machine begins running. The LCD shows the current stage. For example, now it says function wash. The fan turns on. This simulates the motor. It continues to run while the washing stage is in process. The Once the washing process is complete, the machine automatically transitions to rinse. The LCD updates to show function, rinse, and then fan behavior changes depending on the stage. After rinsing, the process moves to spin. The LCD displays function spin. After all stages are done, wash, rinse, spin, the LCD displays program completed, remove clothes. At the same time the fan stops, the buzzer sounds continuously to alert the user that the process is finished. After completion, the system automatically resets the program selection screen. It is now ready for the next wash cycle. Now let me show you a demonstration while keeping the door open. So I will press switch RB0 to open the door. As you can see, the machine has now stopped running. The buzzer is beeping continuously and the LCD displays a warning message, door is open, please close. The fan has stopped working immediately, meaning the motor is halted. The timer is paused so the washing cycle is temporarily stopped. The buzzer stops. The buzzer sounds continuously to alert the user that the door is open. This is a safety feature built into the system to prevent the machine from running when the door is accidentally open. The process will remain paused in this safe state until the door is properly closed again. Once I close the door, the buzzer will stop, the warning will disappear, and the process will resume exactly from where it was paused. Through this internship and project, I learned how to program a microcontroller using Embedded C, how to interface peripherals like LCD, keypad, buzzer, and fan, how to use timers and interrupts for real-time control, and I applied a state machine-based design for managing process step by step. This project helped me understand the real-world application of embedded systems and strengthen my programming and debugging skills. Also, this internship has given me the confidence to build real-world embedded systems with a clear understanding of both hardware and software integration. Thank you for watching my presentation. I would like to thank Emertxe and all my mentors for this great learning experience. This project has helped me gain hands-on skills in embedded system development. Thank you once again.